Hi everyone, back. So we are here for an afternoon of practical applications of geothermal projects. So this half day is to be clear, is common to both events, to the European Geothermal PhD Days and Geothermal Winter School of the MID project. And this later event will follow for the rest of the week. So this will be properly introduced tomorrow. For this afternoon, in the first part, we will see 4 presentations of case studies throughout Europe. So shedding light on remarkable demo sites that have brought significant knowledge on the deep geothermal systems for provision of either electricity or heat. And in the second part, after the break, 3 virtual site visits are organized. And therefore, you will attend several live or recorded presentation of surface geothermal installations dedicated to heat or power production and providing a large range of quantity of energy that is generated. So this is the program, and just for technical aspects, you can relax now because we will also stay in this Zoom room for the rest of the day. So don't go to PhD Talent anymore. Just listen carefully and peacefully to all the talks. But you can ask questions whenever you want and also raise your hand to take the floor. If you have questions, I will transfer it to Albert, who can also see the chat, the Q&A box. Albert Genter, our MID project coordinator. Thank you for accepting to be chair for this session. So Albert, the floor is yours, and you can present with your first speaker.
Thank you, Xavier. So good afternoon, everybody. So I'm very pleased to chair this Demosite session because demonstration is very important for geothermal energy. We need to demonstrate that it works, and we have real concrete and tangible sites. So for starting this session with the 4 presentation, I'm very happy to host Professor Thomas Kohl. So a few words about Thomas before he can present his work. So Thomas graduated from geophysics in Karlsruhe. After he made his PhD and his habilitation in ETH Zurich, he was also the CEO of a company named Geowatt in Zurich. And 10 years ago, roughly, he moved back to Karlsruhe, who he became the head and the chair of professorship in geothermal energy. So he has a team with a very good scientific reputation. And as you know, Thomas is also very engaged in the Rhine Valley. He was very engaged, still engaged with his team in Souls, so for a site, but also he worked in Rittershofen and other sites. So I will not detail all the CV of Thomas, but I would like to thank him to be there today. And to Thomas, we report about up Rhine Valley and also mention area, what main result, and also I'm sure he will present what his team is doing, which is very valuable for industry and for the scientific community. So Thomas, roughly you have 20 minutes of presentation, and after I guess that you will have many questions from the audience. So Thomas, please. Thank you again, and the floor is yours now.
So thank you, Albert. In my presentation, I will not focus very much on our work here. I think it is so specialized, and I rather tend to give you an overview. And I think for the European PhD days, it might be good to provide perspectives, also perspective for work. Why are you doing and why are you working in this area? And you hear so many negative aspects, and I just would like to provide you some positive aspects, how development is going to take place. And I would be very happy if you can also, if you ask me later on questions on this, I will be available for the next half hour after the talk as well as further on. So please understand, I would like to review a little bit the history that we have. And I think it's a good history in geothermal. So let me start with the presentation. I hope you see all the presentation right now. So I'm going to talk about the deep geothermal projects in the Rhine Graben area and the Munich area that we have here, out of a kind of a French-German and pure Bavarian perspective. Now, the background to geothermal is the stress state. And there is, of course, a critical stress state. And as everybody knows, and most of you will know, that we have a north-south tendency in the stress field in Europe, which manifests very well in the Rhine Graben area, or that manifests very well in the Bavarian area. And this is a tectonic movement from Africa through the Italian arc into the Alps that creates this huge stress field. And everything that we can see, we have the manifestations at surface where we can identify also normal faulting, transfer faulting, thrust faulting. And these aspects are a major and also will extend down to greater depth. Now, when we look here in the Rhine Graben, I first will focus on the Rhine Graben and then we go into the Munich area. When we look on the Rhine Graben area, so it is an active tectonic area. Okay, so there's movement, we have a normal fault regime, we have a transfer fault regime, and the Rhine Graben is bounded between the Black Forest and the Vosges Mountains, has an extension of 350 kilometers in north-south and 50 kilometers in east-west direction. And we have a couple of geothermal projects, and we could even have much more. So there is really new ideas on how to develop. So right now there's a mixture of hydrothermal projects, like for example Rhine and Postfossil, the pure hydrothermal projects, and we have a petrothermal project like Sulz, and we have a huge number of mixed projects like Rittershofen and Insheim and Landau, where the fluids can come out of crystalline rock or can come out of Buntsandstein sedimentary rock. So there's this kind of mixture, which is very typical for the Rhine Graben area. And in this extensional tectonics, we have a tendency for opening. And opening is of faults in the underground is always associated to a probability increase. And this probability increase manifests itself through temperature anomalies. So what we see here on the in the lower part here, north of Hagenau, this is the Sulz area. This is the temperature anomaly of Sulz that is visible here. We have more to the north, there's a temperature anomaly of Landau. And of course, there are other temperature anomalies that have not been drilled at the time of the picture. But it is very clear that these temperature anomalies are created by convection cells. And one of these convection cells is what you can see here on the right. So it is a very typical hydrothermal situation. We have a diffusive flow, heat flow at the top, and then we have convective flow. In the case of Sulz here, what I show between 1,400 and 3,800 meters, and then it continues again as a diffusive temperature flow, heat flow. And this diffusive flow indicates more or less low probabilities. Convection cells indicate high anomalies, high probabilities, and also create these kind of anomalies. So the tectonics is linked to hydraulics, and the hydraulics is then creating convection cells. So this is more or less the motivation for geothermal in the Upper Rhine Graben. So the Upper Rhine Graben has one of the highest temperature anomalies in Europe, in Central Europe, maybe, and this is more or less even comparable to what we have in parts in the United States. You know, the basin and range situations where we also have extensive tectonics, we have similar situations. And so it is one of the largest temperature anomalies in Central Europe, maybe the largest one. And we have also what we do from side of KIT is we have a lot of cooperation. And these cooperations are cross-border cooperations. These cross-border cooperations go to the Strasbourg, go to industry, or go also to Darmstadt, the Technical University of Darmstadt. So we have these kind of cooperations with academia and with industry. And this is very important to say. We cannot stay on our own, but we need to have cooperation. Industry is providing very important data for us and provides background on our scientific work. This is essential. So this is also an essential part of our strategy that we have here at KIT, where we are working in the frame of the Helmholtz research and on the frame of the pure academic university research. So we have two aspects of our research. The one is the Helmholtz aspect, and the other is the academic research at universities. We can even look a little bit closer to these temperature anomalies, and this is a situation at Landau that has been evaluated in the past. And so when we have these north-south striking faults because due to the stress field that we have with Rhine Graben, so these are critical faults, and these critical faults create temperature anomalies, and you can see this very nicely on this left picture. And we have measurements on these variations along the fault, and we see that along faults temperature is rising and going up and going down, and this is purely related to convection and purely related to high probability. So this is, in a way, in Europe, one of the unique situations. And on the right, you see the fault patterns that manifest in the Rhine Graben and that have been very well investigated in the past through the oil industry, and right now they're investigated by 3D seismics in geothermal development. Nevertheless, my message to you is we need geomechanics. Without the understanding of geomechanics, we will not be able to understand geothermal systems. Now, let us give a snapshot of different projects. I'm not so sure if all the numbers are right that I have here, but we have some projects on electricity production and heat production. There's even a mistake, heat, but they are at different depths, down to 5 kilometers, at different temperatures, at different flow rates, and they are operated by a triplet or by a doublet system, and some of them are really in operation. Others are right now still in the progress stage, so we don't know what is going on in Brühl right now. So there is a tendency that this will become a key part of a major, huge heating project in the future. But we also have a number of projects that have been stopped, like recently the Wendenheim project. I don't expect that Lindenheim is going to that it will start operation one day. Speyer stopped because of oil recovery, and like Wendenheim, Basel was the first one where we had major earthquakes, and also earthquakes are of course linked to geomechanics. So again, without the geomechanical aspect, we wouldn't have these earthquakes created in here. And they are the major barrier on geothermal right now. And as everybody knows, public want to understand if the projects create earthquakes. Just give you two snapshots of the geothermal projects here in Bruchsal. So the operator is ENBW. And they are reaching depths of 2,000 meters something, and very low temperatures up to now. So this is a test, more or less a test operation that continues for a while. Another project that is quite well in operation since many years right now, and it's very reliable, it's the Insheim project that is operated by Pfalzwerke. And this project is very close to KIT, by the way, and we have a very good relation to that project as well. We have, of course, other good relations to other projects like in Sulz and Rittershofen from ASG, ES, and but these projects will be introduced to you by Albert tomorrow, I think. So therefore, I don't speak about these projects here. But I would like to focus on one point. We have all these projects, many projects that are successful. They have a kind of a stepwise project development. And in this project development, they made a learning curve. And for example, one of these learning curves that was done in Sulz was the circulation testing in 2010, where 11 months of operation were the system was operated with a producer production in GPK2 and injector in GPK1, GPK3, and a flow rate of roughly 80 liters per second. Injection pressure was below 5 bars, also below the level that was targeted right now in Bentenheim as well. In this period, people learned how to reduce earthquakes, okay? Not only in number, but also in magnitude. And this is very important. So, of course, the learning curve came that at highest flow rate, the highest earthquakes occur. At highest flow, shut-in conditions, earthquakes can occur. And this is part of the learning curve that you only can get on site. If you don't do this, so this is an example here of Basel. I could have even added right now the Bentenheim project as well. If you try to force your project development by the end because you're running out of money and you want to just achieve it and you don't have this learning curve, then you will create seismicity. Yeah. Okay. In this case, in Basel, there was a maximum flow rate of 63 liters per second. And there was a continuous increase of seismicity. You even can observe this. So there's a whole history behind until you reach this kind of damage event, this damage seismicity. And you not only can look focusedly on, oh, there's seismicity, but there's a history in behind. And you have to understand this history on the local site. And this is very important. So, well, there are important barriers in this development. So we have, there are large, well-established operators right now, like ES or ENBW, that have very little problems. Or Pfalzwerke, I don't know. So they had really the perspective to develop their project at long term. There's also a success when going into transparency on the local support that people have, that the project has in Sulz, for example. But there are major barriers. The major barriers is that the aspect of communication is typically underestimated. So we have learned also that we need to make informations, and we can only leave over to action groups, to Bürgerinitiativen, to have these, to spread information. The operators may have overestimated the secrecy in the past. So there's a missing transparency. We have to understand that many of these projects are prototypes. So the prototypes are typically done in cooperation with others. And the economic constraints, as I said here for Basel, but this is definitely also true for Bentenheim, are true for these major impacts. When there have been cooperations with scientific institutions, typically this was beneficial for the project. There are also common commitments between industry and universities that can be done. And we should not leave over the spreading of information to these civil action groups that then may misinform the public. So this is a major danger that I see. I would like you to give a positive example. This is Rhine, the Rhine project, for example, which is 3 kilometers out of the deep heat mining project. They had a good, transparent communication strategy, and even 2 years after the seismicity that occurred, the people in Rhine, they voted for the extension of their heating grid, geothermal heating grid. So this is a big success, and it shows that you can convince people on these aspects. we have also new perspectives in geothermal. This is what we develop here at KIT. So we have the new Deep Store project at KIT, in which we want to store seasonal heat. Excess heat of summer, we want to produce in winter. This is a kind of battery. This is a thermal battery we can use our underground. We do this in cooperation with industry, with NBW as well. And so these batteries have an efficiency of more than 80%. Okay, so we can preserve the heat of more than 80% over a year. If we make large projects, this is also economic. If we go into the storage project, making it large, we can really go into economic size. This is also the message that I would like to give you. At KIT, we have a lot of information. We have also the Rhine Graben. We typically have a lot of information out of oil industry. So there's a whole sequence of boreholes that you see here, where we have data. We have a lot of data available, and we want to extend these data onto our campus that is here shown in green on the path. Okay, so we have these data, and we want to infer we want to create in the tertiary rock a storage system. And the tertiary typically has very clayey material as the Rhine Graben, but we have definite lenses, permeable lenses, and these are these very tiny reservoirs in which oil has been produced in the past. And we want to go exactly into these systems. We have feasibility studies done on this aspect, and they show that there's a broad perspective. So we won't just go into the same reservoir, not in the oil part, which is more to the left. We want to stay in the water part of these reservoirs on the campus. So, but this, because we are exploiting the same reservoir rock, so this also demonstrates transfer from the into the post-fossil age. This gives a perspective for geothermal. We need to have innovative geothermal usage as this. We have very close collaboration with civil action groups, even, by the way, that are supporting our activities on research, and this is very important. And of course, we have numerous scientific challenges to solve in this project. But you see here, this is the campus north. We have our district heating grid. We want to go into these lenses, into these small reservoirs here. And we want to drill with oil technology into the same reservoir rock. I would like to go right now onto a definite success story, the success story of the Bavarian Molasse, Munich area. And typically, the Malmkarst is here produced. The Malmkarst is, if you go to the south, the Malmkarst is dipping to greater depths, and it reaches south of Munich depths of 4,000 meters, and it reaches north of Munich depths of 2,000 meters. So Munich is a little bit in between, roughly 3,500 meters. This is where this huge aquifer is, and it's a very high producing aquifer with flow rates of up to more than 100 liters per second. This is the situation around Munich. You see the Munich area here, and the red ones are all projects that are in operation. The green ones are projects that are planned. There are some failures as well. Here is the one from one of these failures, and I think this one is also a failure. But otherwise, it's a kind of success story what we have here. In total, there are 24 projects with doublets, triplets, and 4 wells, boreholes. And right now, every second, 1,600 liters are circulated in the underground. I have to check my stop here. Typically, they're producing out of the Malm Aquifer. The Malm Aquifer is a highly karstified system that used to be a coastal area at the times of its origin. It still has today a very low salinity, and it is a huge drinking water potential drinking water aquifer, and so the people have to combine drinking water needs to geothermal needs, and so this is different from the situation in the Rhine Graben, where we have highly saline situations. In the Malm, they are the water has drinking water quality and need to be protected as well. So it doesn't make things easier. There is the big vision that in 2040 or even 2035 right now realized, the whole of Munich will be heated. District heating grid of Munich will be heated through geothermal, or mostly through geothermal. So this is really a big perspective on the geothermal development that will take place. But there also have been earthquakes. And so we have faults in this Karlsruhe Aquifer. There are faults like what we have here, a fault right through the town of Munich, and we have here in Unterhaching another fault. We had earthquakes here in Poing. There were earthquakes in Unterhaching. Minor earthquakes have been felt and created trouble in the communication as well, and so they needed to be investigated. And we had the task to do this, and so Robin Seitel, he, our PhD student, or former PhD student, he's decided to make a probabilistic approach, because we don't know really on the cohesion, we don't know really on different parameters, geomechanical parameters. And so when looking into the strike direction of these faults, and which are close to the operation, we see that under a given uncertainty, we might have some projects where we can create earthquakes. So these are earthquakes where we can, which have a potential strike direction in which earthquakes can be generated under the reason of different cohesion and under different injection scenarios. And so especially the area in Unterhaching is what is very well understood. So we can really understand why we had these earthquakes in Unterhaching, because there are parts of the fault that are really critically stressed and maybe may create earthquakes. However, may fail critically. But however, these there are right now new strategies that out of these production, so they will invert injection and production wells, and out of this learning curve, no further earthquakes has been fortunately been created in Unterhaching right now. And the huge perspective is what happens in Munich right now. This is my second last slide. Right now we have in Munich itself, there's a big project with 5 wells already. Other wells are going to be drilled down with a total length of 6 kilometers. They're spreading out of Munich, in Munich, through the town of Munich. And so they will start operation in a couple of years if they're going to be tested carefully. But they require, of course, monitoring. This is also a project in which we are involved. So the monitoring under urban conditions is a key aspect of the research that has to be done in Munich. And
Thomas, you need to conclude.
In future, even the other projects, they will be linked to Munich. I may conclude. We need to have new scientific approaches in future. Monitoring and transparency in this aspect. We need to counter the societal aspects, especially have to take care of the aspect of induced seismicity. We understand the processes. This is important. So in each of the cases, we have understood the processes which are responsible for it. The problem still is on the forecasting, but forecasting need to be done with local testing. I have explained this. And we have to benefit from the learning curve. In Munich, we have a huge learning curve out of the 24 projects. And we also have to learn out of successful projects in the Upper Rhine Graben. And that was, I want to stop. And thank you for your attention.
Thank you, Thomas. So I think there are some questions in the chat. So maybe I can rephrase some questions. So some questions are about, I would say, mainly question about money, I would say. So could you elaborate more on, elaborate more on the longer, more expensive case-specific seismicity monitoring practice would you suggest? So the question is, do you have some technology for doing monitoring of induced seismicity? We could be very helpful for limiting, I would say, or for preventing or for measuring earlier, or to be able to help to prevent, I would say, a large earthquake.
So this is exactly the case of the, so we have two aspects in this. The one is what we do in Munich. So we have on the fiber optics, we are monitoring, we have a testing facilities to monitor seismicity on fiber optics, together with satellite measurement of uplift. That the more the expensive tools are not so necessary, so we are doing both together, but with the wish that in future we have very cheap monitoring on site. And the other is that what we do on the Citizens for Science aspect, on Science for Citizens, that we want to spread very cheap seismometers into local buildings, that we have something that where the operators can control possible damages, but also where the local population has a chance to do to look on the local seismicity in their house. So we have these two aspects are connected to it. So we need to have cheap monitoring. Yes.
Okay, there is about seismicity. There is another question that after the Vandenheim earthquake, do you think that there is a future for geothermal energy in the Upper Rhine Valley? Maybe
I
from
think
an academic
it might be a problem on heat, on electricity and power production. Maybe power production can only come back after another 10 years. However, I think especially in Germany, there is a huge need for having a seasonal storage, and the seasonal storage is definitely a future perspective. Also, the production of flow at moderate flow rates. And heating just requires moderate flow rate. They don't require high flow rates. And I think if we can reduce and get technologies to reduce flow rate and to make systems economic on moderate flow rates, then we can have success in the Rhine Graben.
Okay, maybe a question about storage. Is it cost competitive, especially compared to battery? Do you have an idea about that, the cost to store energy or to store energy in battery? You have some ideas about that?
So if you look, the underground is a huge battery. You will not be able to have a heat battery that is lasting a half year for the heating needs, for the huge amount of energy that we require in winter. And so we will not have a typical lithium battery for producing heat. This definitely will not be the case. So we have a very few options right now how to store the heat. And in this case, I see we can collaborate with photovoltaics. We can collaborate with wind energy on storing this excess heat from summer into winter. So we don't. This is what we say is the different aspects can work together and jointly realize the energy transition. So, of course, we do this right now not on an economic basis. It's research. We have a research project. This is definitely not economic, but we want to demonstrate it is possible. And once we've demonstrated, then the industry has to come in and has to contribute more.
Okay, I see some questions, Thomas, so I would like to please answer shortly. So one question is about also economics of project. What do you think, what is the main, I would say, component in terms of project drilling depths, fluid composition, meaning corrosion, heat rock conductivity? So what are the main part of it we could reduce the cost somewhere? Do you have some idea in terms? based on the research which is done now?
Yeah, it's not an easy question. Of course, the things are linked all together. I mean, permeability is a key aspect, and having a good thermal underground, things need to be done in parallel. I mean, we need to have laboratories where we can learn how to stimulate rock more. This is definitely a research project aspect as well. We don't have always the conditions of Munich or in Paris, so we need to have we need to learn how to make the underground probable in order to use the huge storage facility under our feet. I mean, there are lots of research.
There are several
there. I mean, this is definitely, we have successful industrial projects, but we still have a lot of research aspects.
Yes, thank you. And maybe to finish, there are some questions about social acceptance regarding induced seismicity. So some of the question or let's say how we can progress on that, because generally the data are in the hand of the industry. So how do you see how we can improve social acceptance? You mentioned transparency in presentation several times. Do you have idea on that topics? How we can progress on that topics? To organize more public conference, or to be more transparency? It's a message.
Yes, I mean, this is I'm convinced that we need to create the transparencies. I mean, it's not only a civil action group that is opposing geothermal. They might be even very much interested in these phenomena in underground. And if we provide them the tools to monitor themselves, we can include them in the project. So there are some aspects where we can learn how others have done in the past on critical technologies and how they could reach or change the opinion of different people. So I think we have to go into this, and I just was mentioning these raspberry shake seismometers that we want to distribute and that we are checking right now in a project. And that we want to distribute to these people even. I mean, I wouldn't mind to go to one of these civil action groups and say, here in your house, or 10 houses, select 10 houses, and we give you these raspberry shakes that you can monitoring. We will provide you the data. But this gives security to the operator as well, that there's no damage created, like what had been done in Landau, and one guy was shaking up the whole community. So if we can manage this is much easier. Okay, so nice answer. So maybe I will stop the discussion now. You can have a look, Thomas, if you want. There is a question. Okay, I will try to answer. There are some other questions from Yassine about geophysics and other people, but we need to move on. So I would like to thank you very much, Thomas. Okay. I know you will stay a bit with us for some minutes. Yeah. So thank you very much, and I will